Hello friends, and welcome to a lecture on operation research. This is Professor Arvind Prasad. Today we will learn about linear programming, and this lecture is going to be a general introduction to the concept of linear programming. So let's go ahead and look at a problem. A management has taken over a loss-making company. The company has 3 plants. Plant number 1 produces aluminum frame. Plant number 2 produces wooden frame. Now both aluminum frame and wooden frame are used in the production of making glass windows. And plant number 3 only produces glass. But because it's a loss-making company, it was unable to produce glass windows. Now the operation research team of the new management, it visited the plants and it found that per week, plant number 1 had 4 hours of slack time. That is, for 4 hours per week, they did not have any job. Now plant number 2 similarly had 12 hours in a week where they did not have any work. Plant number 3 did not work for 18 hours per week. With the machinery available in plant number 1, it required 1 hour to produce a batch of aluminum frames. And with the machinery available in plant number 2, it required 2 hours to produce 1 batch of wooden frames. And with the machinery available in plant number 3, where they could produce windows because they also produced glass, so they could take the glass and fit the frames on it. Now, to produce 1 batch of aluminum frame windows, it required around 3 hours. And to produce a batch of wooden frame windows, it required 2 hours. The marketing team found that if we sold these windows in the market, the aluminum frame windows would fetch us 3,000 rupees for a batch, and it would fetch us 5,000 rupees for a batch. The problem just posed can mathematically be put up this way. The decision variables that we have are x1 and x2, where x1 is the number of aluminum frame or the batches of aluminum frames windows that you can produce, and x2 is the batches of wooden frame windows that you can produce. The objective function is z is equal to 3x1 plus 5x2. Well, 3 stands for 3,000 rupees multiplied by the number of batches of aluminum frame windows that you produce, plus 5 stands for 5,000 rupees multiplied by the number of batches of wooden frame windows that you can produce. Obviously, the constraints are that you cannot produce more than 4 batches of aluminum frame windows. Now, why is that? Because the slack time available in plant number 1 is only 4 hours. And it takes 1 hour to produce 1 batch of aluminum frame. So that makes it the maximum supply of aluminum frames per week that you can get from plant number 1 is just 4. Now in plant number 2, the slack time is of course 12 hours. But it takes 2 hours to produce a batch of wooden frame. Now the maximum supply of wooden frame per week can be 12 divided by 2, that is only 6. Now let's come to plant number 3. In plant number 3, the slack time available is only 18 hours per week. So the maximum that we can have is 3 multiplied by x1 plus 2 multiplied by x2. That is, 3 is the number of hours that we have to spend in assembling the aluminum frame windows, and 2 is the hours we have to spend in assembling the wooden frame windows. So x1 is the batches of aluminum frames and x2 is the batches of wooden frames. Now we put glass in these frames. When we put glass in these frames, it requires 3 hours to make one batch of aluminum frame windows and 2 hours to make one batch of wooden frame windows. And the maximum slack time available in plant number 3 is just 18 hours. So how do we solve this problem? Well, such simple problems which have only 2 variables or 2 decision variables, they can be solved graphically. So what we do is, well, there we have the decision variables x1 and x2, objective function I have copied it out, the constraints I have copied it out, and we make 2 axes. The horizontal axis is decision variable x1 and the vertical axis is decision variable x2. Now first we draw the constraints that we have. Because x1 cannot be greater than 4, we draw a line for the constraint. x1 is equal to 4. It's going to be a vertical line which is going to cut the x1 axis at 4. Similarly, we draw a horizontal line which is going to cut the x2 axis at 6. So these are the constraints that we have put. Now the third constraint that we have is 3x1 plus 2x2 less than equal to 18. So we take it 3x1 plus 2x2 equal to 18 and we draw the line. So that's what we do it. So once we have done this, this is the feasible region, or this is our solution space. Now any values of x1 and x2 within this region will satisfy our constraints. Okay, so finally what we do now is we take values for objective function. First we take the value of z as 10 and we draw the line. As we can see, if the management decides to make a profit of 10,000 rupees per week, this is going to be the line for that, and it is going to pass through the feasible region. Now we can see here it passes through the feasible region and there can be multiple solutions of x1 and x2 which satisfies this objective. If the management thinks of making a profit of 20,000 rupees per week, so we can draw this line. And as we can see here, this also passes through the feasible region. And there could be multiple solutions to the objective that management ends up making 20,000 rupees every week. Now it's very simple to do this on a graph paper. All you have to do is make the axis for x1, make the axis for x2, draw a line for the constraints, and whatever area you get within the axis and the constraints is the feasible region. Now you take the objective function, give a value to the objective function and draw the objective function. Draw the line for the objective function. Mind you, in linear programming, all equations are linear, so therefore they will be straight lines. Similarly, you take another value for the objective function and you again draw the line for objective function. Now you keep moving this line till it just touches the corner point of the feasible region. Now this is the solution because this is the optimal solution. If you try to make a profit greater than 36, well, this line would shift further ahead and it would not be in the feasible region. That is, it would have been an infeasible solution. Now, why would it have been an infeasible solution? Let's look into it. So, of course, here the corner point is 2, 6. Now, 2 multiplied by 3 plus 6 multiplied by 5 gives you 36. So, let's have a look at it. What is a feasible solution? What is an infeasible solution? And what is an optimal solution? Well, solutions which pass through the feasible region are known as feasible solutions. They need not be the optimal solution. Why? Because as you can see here, a profit of 10,000 per week can also be realized in the feasible region. A profit of 20,000 rupees can also be realized in the feasible region. Feasible region here gives you the constraints of the plant, that is the hours available or the production capacity available in the plant. Your objective is to use the maximum hours in the plant and earn profit. Therefore, as we move from the origin parallel to these green lines, we come to point number 26, which gives you the optimal solution. 2 and 6, when put into this equation, the objective function equation yields us 36,000 rupees. That is, the maximum profit per week the management can realize is 36,000 rupees. Well, what if it tries to get more profit? So the line will shift further to the right. Now here you need to understand that this is an infeasible solution. Why? Because the capacity of the plant is such that it cannot produce that many batches of aluminum and wooden frames. That is, plant number 2 cannot produce that many number of batches. Why? Because it can, though it can produce, in line red, you can see it can produce. But what would happen? Plant number 3 wouldn't be able to produce that many number of glass windows. So this is an infeasible proposal. That is, making a profit of around 50,000 rupees per week is just an infeasible proposal. So that was all about a gentle introduction, but a very solid one and a very clear one. Introduction to linear programming. In linear programming, as you can see, the constraints and the objective function, they are linear equations. That is, the greatest power of the decision variables here is 1. So that was all about linear programming, guys. If you like this video, do subscribe my channel. And of course, send it over to other people who would be interested in learning this subject. This playlist is all about operation research. Keep watching. And please ask others who benefit from my videos, that is, to whom you share the link, to also subscribe my channel. Goodbye, friends. Have a great day.